In this lesson, we'd like to determine how to find an inverse function. But before we do so, we need to first determine which functions are even able to be undone or reversed so that those outputs take us right back to the inputs and we still have a function. So what that means is that if we have this particular mapping that takes each value in the domain to each value in the range, then that would imply that each of the inputs for the domain give me a particular output for the range. And that's why we know that f is, of course, a function, since every input corresponds to exactly one output. Now, if this function has an inverse, that would mean that each value in the domain becomes an output, while each value in the range becomes an input. So we're switching the x and y values so that each of the domain values now takes me back to a new range value. So we can see that this does have an inverse because for the function f, 0 takes me to 3, while for f inverse, 3 takes me back to 0. For the function f, 4 takes me to the output of 9, while for f inverse, 9 takes me back to a new output of 4. So if we take a look at another example, let's call this function g. G is also a function because every input in the domain gives me a single output in the range. So this particular function, this mapping, is in fact a function. So let's switch the domain and range values and see what happens if 3 takes us back to 0. 0 now takes us to 1 and 4, and 9 takes me to 7. We should realize right at this point that this is no longer a function. So if we're trying to invert what the original function did, then this right here does not give me a function because 0 takes me to 2 different outputs. So the question then is, what criteria is necessary in order to create a function when we inverse the process? Well, the function must be what we refer to as one-to-one. If we take a look at what this means, this shows us that each input needs to determine a different output. So we know that in order to be a function, every input needs to take us to one single y value. But in order to be a one-to-one function, we know that every output can't come from more than one input. Now we can see that pretty easily on a graph. This is a function, but we also consider it a one-to-one function because every output along the y-axis is only giving me one single input, or is only coming from one input. That's why we refer to this as the horizontal line test. We know that the horizontal line, or every y value, is hitting the function at one point. Therefore, this is a one-to-one function. But what if we take a look at another function? If we were to call this function g, we can realize that this is a function since every input gives me one output. This passes the vertical line test. The problem is that this function is not one-to-one because for each y value, I know that I'm going to be hitting 3 different inputs. Therefore, even though this is a function, it is not one-to-one. So what we've seen here is that not every function will have an inverse function. Our job is to find the inverse. So let's think about what this means. For a one-to-one function, we should recognize that the domain of a function f will always become the range of a function f inverse. And likewise, the range of some function f, all the outputs, become the new domain for f inverse, which means that the outputs become the inputs. So in general, every x should give me a y value for a function, while if we revert or invert that process, each y value needs to take us back to an indicated x coordinate. So to give a particular definition of the inverse of a function, we're simply going to recognize that if f is a one-to-one function, if we check that originally, and f has all of the ordered pairs x comma y, then we know that the inverse of f, which now has this new notation, is the one-to-one function consisting of the ordered pairs y, x. So for every point x comma y on the function, f inverse of x has the point y comma x. So we're simply interchanging the coordinates of each ordered pair. And now we can recognize that f inverse has this new notation. We simply call this f inverse of x. Now let's be very careful, because this little quantity here, this -1, is nothing more than a symbol that denotes the inverse of a function. That -1 does not denote an exponent. So we can't think of it as an exponent like we would by taking the reciprocal of a function. Okay, so f inverse of x is not the same as the reciprocal. So let's look at how to actually find the inverse of a function. Okay. If we have a function called f of x, recall that x is the input while f of x is the y, or the output. So f of x always stands for y because f of x is the output of our function when we plug in x. But what that implies is that f inverse of the output, which was y, is now going to take me back to my input of x. So if a one-to-one function takes an input from x to an output of y, then this process is simply reversed for an inverse function. So let's talk about how we can find the inverse of this function here, f of x equals 2x minus 6. We first check to see if the function is one-to-one. Now remember, what that meant is that the function needs to pass the horizontal line test, but that's only possible if we could actually understand what the function looks like. We should realize that this function is a linear function, and linear functions do in fact pass the horizontal line test. Every output only comes from a single x value, or a single input. So yes, this function is in fact one-to-one. Once we determine that the function is one-to-one, we're simply going to replace the f of x with a y. So now we have the equation y equals 2x minus 6. Now recall that on an inverse function, all the inputs and outputs have reversed roles. So the next step is simply to interchange the variables of x and y, which makes all of the outputs become the new inputs, and all of the original inputs become the new outputs. So this technically is already the inverse function, but in order to actually find the inverse function itself, we solve for y. So here, we're going to simply add 6 to both sides to get x plus 6 equals 2y. And to solve for y, we're going to divide by 2. Now we should typically simplify this if possible, although again, we have solved for y. We're going to separate this to make it 1/2 x plus 6 over 2, which is 3. So if f of x equals 2x minus 6 is the original function, the function that will take me back to the original outputs will now get me what we refer to as f inverse of x. So we could think about this in one particular way by just choosing for the original function 1 or 2 inputs. So let's go ahead and pick an input of 4. If we let x equal 4, then 2 times 4 is 8. 8 minus 6 is 2. So the input of 4 gave me an output of 2. That means for the inverse function, an input of 2 should take me back to an output of 4. So let's see why that works. 1/2 times 2 is 1. 1 plus 3 gives me 4, which took me back to the original input. This is what we refer to as an inverse function. To see what's actually happening with an inverse function, we can often think of this as a machine. So keep in mind that for a function machine, you can take an input of x, the machine or the function does some job, and outputs f of x. So what does an inverse machine do? Well, you can think of an inverse machine as perhaps a mistake machine. Maybe you were working in a machine shop and you put in a piece of plastic. You were supposed to get out a fork, and unfortunately you got out a plastic bottle. So what would this machine actually do? The inverse machine would take your mistake or your bottle, you could put it into the mistake machine or the inverse machine, and it will undo what f of x just did. It should get you right back to the original input. So if x is plugged into machine f to get f of x, now I plug f of x into f inverse, and I get f inverse of f of x. However, we know that that should be the original input, so that must mean that the output should be x. And this is actually how you can check to see if if two functions are inverses of each other. In other words, f inverse of f of x must equal x, but also f of f inverse of x should equal x as well. So I simply need to apply these two compositions of functions, and if both of them give me the original input of x, I know that the two functions are inverses. So let's try that with this particular function here. So if f of x is 2x minus 6, we found on the previous slide that f inverse of x was 1/2 x plus 3. We already know they're inverses, but let's see why. If we were to take f of f inverse of x, that just simply means to take f inverse of x as the input to the function called f. So we replace f inverse of x with 1/2 x plus 3. We can now take 1/2 x plus 3 and plug it into the input of f of x. So that gives us 2 times the quantity of 1/2 x plus 3 minus 6. So as you can see, we put the function of f inverse into the function of f. And when we distribute, notice that gives us x plus 6 minus the extra 6, which gets me right back to what I started with, or the original input. Now we would think that these are inverses of each other, but all this shows us is that f inverse is the inverse of f. We want to determine if f is the inverse of f inverse. So we're now going to plug in f of x as the new input to f inverse. So we replace f of x with 2x minus 6, and we can now take that quantity and plug it into the function f inverse. So we get 1/2 times the quantity of 2x minus 6 plus 3. So we should see that we plugged f of x into the function f inverse of x. When we distribute the 1/2, we get x minus 3 plus 3. And sure enough, that takes us right back to x. Therefore, we know that f of x and f inverse of x are both inverses of each other. So one of the big questions about inverses then is how exactly are the points a, b, which is on f of x, related graphically to the points on BA, or on f of x, BA on f of x, which simply means this. That remember on f of x, if you have the point AB, then f of f inverse of x has the same point where the input and output are reversed. So let's just assume that these are a few points on the function f. Notice that this point 1, 2 will have a corresponding point on the inverse function of 2, 1. If you look at -3, -5, then on the inverse function, you should have the point -5, -3. So let's show where those points would be. We can see that these blue points, if we were to plot -5, -3, compared to -3, -5, there should be some sort of relationship. It looks as if there is symmetry involved. But it's not symmetry over the x-axis. It's not symmetry over the y-axis. One thing I should notice, though, is that this point at -1, -1 is actually on both the function f and the function f inverse, which should be obvious because if I switch the x's and y's, since they're the same, you're going to get the exact same point. So what we should notice is that functions and their inverses are reflections over the line y equals x. So if I were to draw the line y equals x, then by flipping points over the line y equals x, I'm changing all of the inputs to outputs and all of the outputs to corresponding inputs. So if we look at this as an actual graph, then let's assume that this is the function f of x. What we should recognize is that f inverse of x is simply going to be a reflection over the diagonal line y equals x. So that would mean if I have a point AB on the original function, then on the opposite side of this line would be the point BA, the same distance away from y equals x. You could actually see that any point that's on the top side of this function, or on this line y equals x, will give me a point on the bottom side. And more specifically, if you look at any point on the function that touches the line y equals x, then that means that the coordinates are exactly the same. So switching them will also give me a point on f inverse. So if I now connect these points, I get the new green graph, which is considered the inverse function to the function f. So in order to plot inverse functions, all we're doing is switching the inputs and outputs and plotting all of the points that remain.